Hello everyone, welcome to the lecture on uncertainty modeling in AI. And today we are going to talk about Markov random fields, or otherwise known as the undirected graphical models. Of course, I didn't invent any of today's material. A lot of the lecture slides and contents are taken from the textbook written by Kevin Murphy, in particular chapter 19, and the textbook written by Daphne Koller, in particular chapter 4, as well as the unpublished textbook written by Michael Jordan, which can be accessed from this link over here. I also took some of the materials from the textbook written by Christopher Bishop, in particular chapter 8 section 8.3, which can be obtained from this link over here. Hopefully by the end of today's lecture, you will be able to explain the concepts of Markov properties. In particular, you'll be able to define the global, local, and pairwise Markov properties and use it to read off all conditional independences from an undirected graphical model. We'll look at the definition of clique potential functions, which we will then use to parameterize the joint distribution of a Markov random field. Finally, we will look at the differences and similarities between a Markov random field and conditional random field, which are both undirected graphical models. So we'll start off by asking this question: why do we need undirected graphical models, especially since we have already looked at the directed graphical model, or otherwise known as the Bayesian network, in the last lecture? We'll see that the answer to this question is that for some domains, especially for the spatial analysis domains, the requirement for directed edges in the graphical model can be rather unnatural or awkward. An example is what we have seen in the previous lectures, in the image segmentation, where each random variable represents a pixel in the image. And we have also mentioned in the previous lecture that neighboring pixels, they occur as neighbors because there is a spatial relationship. There's some relationship between them. They are more likely to take the same labels than the opposite label. Hence, they are related by an edge in the graph. So in the case where if we were to represent this particular graphical model as a directed graphical model, we would have to assume a certain ordering in the random variable. For example, that x2 will be conditioned upon x1 and so on and so forth in this particular example as shown here. But in this representation, we will see that, however, that for example, in the random variable x8 over here, it will result in an awkward or unnatural representation for the Markov blanket. We can see that instead of this random variable x8 being dependent on the 4 immediate neighbors as represented in this grid-like structure over here, Markov blanket also includes the random variable x12 and x4, which is rather strange because we are ignoring x2 and x14. So an alternative is to use an undirected graphical model, or otherwise known as the Markov random field or Markov network. So in this particular case, we'll represent the undirected graphical model as a graph consisting of a set of nodes and edges denoted by V and E over here. So the set of nodes where each one of there is a one-to-one correspondence with a set of random variable. What this means is that each particular node in the graph here, it represents a particular random variable, for example x1, x2, and x3 in this case over here. And the edges in this undirected graphical model is of course consisting of undirected edges, in contrast to the Bayesian networks. There is no direction. That means that there's no arrow in these edges at all. And since there's no edge orientations in the undirected graphical model, it becomes more natural for some problems such as the image analysis or spatial statistics. For example, the case where we have looked at earlier in the example of the image segmentation, where each neighboring pixel, they mutually influences each other. Hence, the notation of the edge, directed edge, should be dropped. In this case, we'll replace it with an undirected edge, which is more natural to represent the mutual relation between these two pixels, x1 and x2 over here. Another example would be, suppose that I'm given an image with a human in it, and what I want to do here is that I want to deduce, or I want to do inference on the human poses from the 2D image. And in this particular case over here, I can represent each one of this joint in the human as a node in a tree-like structure over here. You can see that each particular node over here, suppose that I denote it as x1, x2, x3, x4, x5, x6, and x7. Each one of the nodes represents the location of a joint in this particular image over here from the human that I see in this particular image. And I can see that x1 and x2, for example, the head of the person is closely related to the neck. One example here would be that the distance between x1 and x2 cannot be more than a certain distance. It has to be within a certain range, and hence there is a constraint between the two random variables that are related by the edge in the graph. And this is more natural to represent this using an undirected edge, because it doesn't make sense to say that the location of the neck of a person is dependent on the location of his or her head. It's more natural to say that the locations of the neck and the head are mutually dependent on each other. Hence, the undirected graph over here would be much more natural to represent this kind of spatial relations between all the joints in the human being, which can be seen in the image. As I've mentioned in the previous slide, that an example would be the image segmentation problem, where we represent each particular pixel in the image as a random variable, and the neighboring pixel, they have mutual influences on each other. What this means is that it's more natural to represent this the neighboring pixel as a undirected graph instead of a directed graph, because there is no topological relation, or there's no particular order in the influence or the dependence of a random variable on the other random variable. Hence, in this case here, we can see that for example, the random variable x8 over here, it becomes more natural to represent its Markov blanket, where we can see that it's immediately dependent on only the 4 nearest neighbor that is connected to this random variable x8 directly on the graphical model. We'll see later when we define the Markov properties that when we condition upon these 4 random variables over here, x8 becomes conditionally independent of the rest of the random variable in this particular graph over here. So in order to read off the conditional independence from the undirected graph, as which is the same concept as the conditional independence which we have seen from a Bayesian network or a directed graph, we need to define 3 properties, and we will see that it's actually much easier to read off conditional independences from a Markov random field or undirected graphical model compared to the Bayesian network, where we seen that there is an exceptional case of the head-to-head structure compared to the other 2 structures in the 3 canonical 3-node graphs, which is the tail-to-tail as well as the head-to-tail structure. But in this particular case, in the case of the undirected graphical model, we'll see that we'll first define 3 Markov properties: the global, local, and pairwise Markov property, and then we'll show that these 3 Markov properties are equivalent. This means that they are the same as each other, and hence we can actually read off the conditional independences from an undirected graphical model with just with just one rule. So let us start with the definition of a Markov property. Given a set of, suppose that we are given a set of nodes which we denote as A, B, and C. So this A, B, and C here, they do not just represent a single random variable, but it's actually a set of random variables. It's a set of random variables which can consist of course, more than one random variables, or one random variables, or even a null set. So in this particular case over here, we say that it fulfills a global Markov property if the set of random variables A is conditionally independent of the set of random variables in XB, given that we have observed the set of random variables in XC. And this is true if and only if C in the undirected graphical model. That means that the set of random variables in C, once observed, it separates, it blocks all the paths from any random variables in the set of A from any random variable in the set of B in the undirected graphical model denoted by G over here. What this means is that there's no path connecting any nodes in A to any node in B. When we remove all nodes in C, this means that we have observed all nodes in the set C over here. An example would be this undirected graphical model, which consists of 7 random variables over here. We can see that the set of A over here, so this would be the set of A, and this would be the set of C over here, and this would be the set of B over here. We can see that once we observe the 3 random variables in the set of C, which we shade this means that we are the random variable x3, 4, and 5, they are observed, and we can see that once they are observed, all the paths from every possible path from any random variable in the set of A, xa over here, it's blocked from the reaching any random variables in the set of xb. We can verify this by checking a few examples. So suppose that we start from 2 over here, the random variable x2 over here, and we can see that there's no way that we can reach x6 or x7 over here, because every possible path from x2, it's blocked by 3, 4, and 5, the random variable nodes 3, 4, and 5 in the graph, and there's absolutely no way for for us to find a path from x2 that reaches x6 or x7 without passing through these 3 observed random variable. Similarly, we can see that if we observe, if we start from x1, there's absolutely no way for us to reach any random variables x6 or x7 in the set of B over here without passing through the 3 observed random variables. Hence we say that this set of graphical model, having observed 3, 5, and 4, it fulfills the global Markov property of XA is conditionally independent of XB given XC. The second Markov property that we are going to look at is what we call the local Markov property. It states that the set of nodes that renders a node XS conditionally independent of all other nodes in G, such that the XS is conditionally independent of all other nodes in the graph, except for the Markov blanket of XS and XS itself, given the Markov blanket, where we use this notation MB bracket XS to denote the Markov blanket of XS. And this graph over here, if it fulfills this condition, it means that the graphical model, the undirected graphical model, fulfills the local Markov property. Let's look at an example over here. It's the same graph that we have seen in the earlier example of to illustrate the global Markov property. But in this case, let us denote xs as the this random variable 1 over here, and the Markov blanket of x1 would be the immediate neighbors. This means that all the neighboring nodes that are directly linked to x1 or xs with a edge in the graph. And in this case, it would be random variable 2 and 3, which is defined as the Markov blanket of xs, or in this case, it's the Markov blanket of x1 over here, or the random variable 1 over here. It would be the random variable 2 and 3. And we can see that once we have observed the condition upon that we have observed the Markov blanket, this means that we have observed the random variable 2 and 3 over here, then xs, which is equals to x1 over here, it's conditionally independent of all the rest of the nodes in the graph except for itself and the Markov blanket. And in this particular case here, it would be the random variable 5, 4, 7, and 6. And indeed, we can also see that in this particular case, all the paths from x1 is being blocked from any random variable in the set of all nodes except for the Markov blanket of xs and xs itself. So we can verify this by starting from the random variable 1 and try to find all the possible paths towards the this set of random variable over here. And we can see that since we have observed 2 and 3 over here, all the possible paths from x1 is going to be blocked from this set of random variable here. So we cannot reach from here, neither can we reach from this direction over here. And hence, we say that once we have observed the Markov blanket, it fulfills what we call the local Markov property, which is otherwise written in this conditional independence statement over here. We can look at another example where let us denote xs with this random variable 7 over here, and its Markov blanket would be the immediate neighbors that are directly linked to xs, which is random variable 7 over here. And in this case, it will be 4 and 6. If we have observed 4 and 6 over here, this means that this set here in this example, it would be the Markov blanket of x7 over here. And if we have observed these two random variables, we can also verify that all possible paths from 7, it will be blocked from the rest of the random variable, which is in this case v, except for the Markov blanket and the random variable x7 itself. And we can see that all possible paths towards this side of the random variables, they are blocked by 4 and 6, and hence this fulfills the Markov property when 4 and 6 are observed. Now the last Markov property that we are going to look at is the pairwise Markov property. In this case, we will look at two nodes that are represented as xs and xt respectively. So in this case here, xs and xt, they are not a set of nodes, they are individual nodes. So this is one random variable, and this is also one random variable in the graph. So we say that these two random variables, they are conditionally independent given the rest if there's no direct edge between them. So otherwise, it's also expressed as this particular conditional independence expression over here. We say that the random variable xs is conditionally independent of xt given all the other nodes in the graph except for xs and xt itself. So in this example over here, we use the same undirected graphical model that we have seen in the previous two examples. But in this case, we let xs be the random variable 1 and xt be the random variable 7. We can see that xs and xt, which is random variable 1 and 7, they are independent, they are conditionally independent of each other when we observe all the rest of the nodes in the graph except for xs and xt itself. In this case, it will be the random variable 2, 3, 4, 5, and 6. And we'll observe all these random variables. We can see that once this set of random variables are observed, this set of random variables here is generally written as all the nodes in the graph except for xs and xt itself, which is in this case 1 and 7, the random variables of 1 and 7. And we can see that once this set of random variables here are observed, all possible paths from xs will be blocked from accessing xt. We can verify this. If we were to move in this direction, we are directly blocked by the random variable 2, which is already observed. And if we were to move in this way, we will be blocked by the random variable x3, which is already observed. Hence, in this case here, we say that all possible paths from xs or the random variable 1 is blocked from accessing the random variable xt, or in this case is random variable 7, when we observe all the random variables in the graph except for 1 and 7 itself. And if any graphical model that fulfills this particular observation over here, we say that it fulfills the pairwise Markov property. So it's obvious that the global Markov property implies the local Markov properties, which also implies the pairwise Markov property by simply adjusting the size of the nodes. But what is less obvious here is that, but it's also true, is that assuming that the distribution, any probability distribution, is more than 0, what this means is that the probability distribution cannot be equals to 0. We'll see later in why is this so. For all x, is that the pairwise Markov property implies the global Markov property.